Hello everyone, I am Madhusudhan Yenuginti. Today I want to talk about device-agnostic DevOps platforms for the AI-driven enterprise. So this is going to be a practical architecture for building containerized, observable and policy-governed delivery platforms at enterprise scale. So for a company like CVS Health, you have pharmacy counter terminals, mobile devices carried by field staff, counter-facing kiosks, cloud-native backend services. So all need software updates under under single compliance and governance requirements. Okay, that's why the title says device agnostics. That's really heart of this. One platform govern the same way regardless of what's on the other end. So before moving to the actual agenda, I want to talk sometime about challenges what we have. Okay, so let's start with why this is hard. Okay, enterprise DevOps has always had pressure, shipping fast, staying secure, keeping the governance intact. Okay, but what's changed in the AI era is the diversity of what we are going to deploy. We are no longer just pushing the code to server, right? So we might be updating the pharmacy counter terminal sometimes, sometimes a mobile handheld device in the field, and sometimes embedded kiosk panel, and sometimes cloud native services, all in the same release cycle we have to do. Okay, when if I think of a real world example, imagine we discover a critical security vulnerability in a shared library. In traditional setup, what we used to do, each device class had its own pipeline. Okay, your security team, what they were doing, they have to coordinate patches across 4 or 5 separate pipelines owned by different teams. Okay, with different criteria, gate criteria. Some patch takes hours, some patches take days. Your kiosk fleet might sometimes unpatched even for a week because nobody wants that pipeline clearly, right? That's a compliance nightmare in the regulated industry. Okay. Each device class have different connectivity, different compute constraints, different compliance requirements. That's the old answer. And we had a old answer that building a separate pipeline for each. So, which doesn't scale. It creates multiple maintenance costs, drifts, and a weak governance because every pipeline becomes its own snowflake. Coming to the agenda, first, device agnostic architecture, which is about standardizing the deployment across all the different endpoint types. Second is about topology models. We got resilient, non-resilient patterns under a common policy framework. Next, containerization practices. Okay, hardened images, least privileged and immutable artifacts are there. So we'll talk about some of the practices. Um, Fourth one about CICD and observability, where pipeline designs, health checks, fleet observability, and cohort alerting. And the last one we'll talk about AI era platform patterns, where aligning the architecture with scalable, secure delivery. Next, we'll get into the first part of the agenda, which is building a device agnostic platform. Okay, so what do we mean by device agnostic? Let's make it concrete. In a typical enterprise, we have 5 endpoint categories, which are fixed terminals, mobile devices, shared kiosks, embedded panels, browser based access. What is fixed terminals? Pharmacy counters, clinical workstations, back office desktops. So in CVS, for example, a pharmacist dispensing terminal runs specialized software with strict versioning requirement tied to FDA compliance. You can't just push an update whenever you want, right? There are maintenance windows, validation requirements, audit trials, all we need to consider. Second one about mobile devices. We have tablets, handheld field worker endpoints. Think of a warehouse associate scanning inventory with handheld, right? Or a home health nurse using a tablet that may go in and out of Wi-Fi coverage throughout the day. That's possible, right? Um, Next is shared kiosks. Customer facing terminals where dozens of users interact per day. The update challenges here is session isolation. You can't push and update mid transaction, and you need to clean the session boundaries. So the next one is about embedded panels. Think HVAC control panels in a facility or a specialized medical device display. Constrained compute, sometimes older OS versions, very specific update windows. And finally, the browser based access, zero install delivery that works on any OS. Okay, the update model is actually simpler here because the device is just a browser, but a governance still applies. The traditional response to this diversity is to build a separate tooling for each. Okay, the device agnostic model says no, abstract the differences, enforce the policy uniformly, and let the platform handle the translation to each endpoint class. So, what is the architecture principle? It's one platform, every endpoint. Okay, this is the core principle. I want to make it tangible. One control plane, policy defined only once. Pipeline logic defined only once. Observability instrumentation defined only once. All projected to every endpoint class. Okay. When we talk about an example, let's say our security team mandates that all deployments must include a software bill of materials, which is an SBOM, as part of our supply chain security posture. Okay. In a siloed pipeline world, you have to go to every pipeline owner, explain the requirement, right? And hope they implement it correctly and consistently. In a single control plane model, you add it once to the shared pipeline template and it enforced everywhere, which is the forms it terminal pipeline, the kiosk pipeline, mobile device pipeline automatically on the next run. Another example I can quote, observability instrumentation, right? If you want every service across your fleet to emit a standard set of health metrics, let's say, you bake that into platform level deployment template, right? Every team gets it for free. You don't have to run a 6 months initiative to get a consistent metric across 200 services. You don't need to do that anymore. This is the architectural bet you are making. Invest into the control panel, invest into the control plane, abstract the endpoints. Okay, the upfront investment is real, but the compounding governance, what we get, and the efficiency benefits are significant. So, moving to the second part, which is topology models, um, I want to talk about resilient versus non resilient topology models. So, under the resilient topology, we have fully connectivity assumed and centralized orchestration. Real time policy is in sync and health telemetry is enabled. And this is suitable for cloud native and always connected endpoints. And in resilient topology, rolling the deployments are with immediate rollback capability. So you can always roll in and roll back. Whereas non-resilient topology, it's always intermittent or offline cable edge environments, and it had to be locally cached policies and deferred telemetry flush, which is again suited for devices like kiosks, embedded panels, and remote sites. And now in non-resilient topology, we have staged promotion rather than rolling deployments, right? So staged promotion with local health verification gates. So high level, this is the resilient topology versus non-resilient topology. And I want to consider an example here. Imagine you push a policy change that restricts a certain network port. Okay, let's say, and legitimate security hardening. Okay, in a resilient topology, what happens? Okay, that policy syncs in seconds, and your health dashboard confirm that compliance within minutes. Whereas in non-resilient topology, that kiosk in the mall or may not sync for 6 hours, right? During that window, it's operating on a bold policy. Your platform needs to account for this, right? Not flag it as a compliance violation, but track it as a pending in. sync is pending basically, right? That's what with a known last sync will also display that what is the last timestamp it had synced. So both topology models live under the same governance framework, but the policy is same. Only the sync and verification timing differs. Okay. Chapter 2 is about containerization, which is hardened containers as the delivery standard. In this chapter, we explain why hardened containers form the foundation of a secure device agnostic delivery model. It also shows how they support consistent, auditable deployments across heterogeneous endpoints without compromising the operational model. So under this, what we have hardened base images and image provenance, non-root execution and runtime isolation, least privilege controls and policy enforcement, immutable artifacts for repeatable deployments. So think about what happened with Log4j in late 2021. I hope you guys remember. Organizations that had clear image provenance, they knew exactly which container image include which version of Log4j, and they were able to identify and patch affected services in hours. That I hope everybody remembers that. And organization that didn't have the visibility, they spent days just doing the inventory. So hardened containers with proper provenance controls the difference between a fast, confident response and a chaotic scramble, right? Four principles drive hardened containers, right? Which I already quoted. Hardened base images and image provenance. Not, you know exactly what's in every image. Non-root execution and runtime isolation. Workloads never run as root, right? Least privilege controls. Capabilities dropped into the minimum required. And finally, the immutable artifacts. Once built, an image doesn't change. That's immutability, right? So let's talk about what are the practices that really matters for the containerization. Um, Hardened base images in practice means starting from distroless or minimal base images. Google's distroless images are common example. So there will not be any shell, there will not be any package manager, no debugging tools in production. If an attacker compromises your container, there is nothing to pivot with. Okay. Let's say a standard Ubuntu base image might have 200 packages installed. A distress image might have 10. That's 190 fewer potential vulnerabilities, right? And next one is about non-root execution. A simple example, if your containerized web server runs as root and there is a path traversal vulnerability in your application code, an attacker can potentially read or modify any file on the container file system. And if it runs on a non-root user with a read-only root file system, okay, the blast radius shrinks dramatically. And if it is a Kubernetes pod security admission policies can enforce this at a cluster level, let's say, okay. So it doesn't depend on developers remembering to set the Docker file. So that's about non-root execution. Next practice is least privilege controls. And here also a concrete example is like dropping the net raw capability from containers that don't need raw network access. So most of the application containers don't need it, but it's included by default. Dropping it prevents a whole class of network-based attacks. Pair this with Kubernetes network policies that restricts which pods can talk to which, and you have significantly reduced the lateral movement risk. And the last practice, I would say, immutable artifacts. So typically, we tag our images as latest in production, right? With the reference of my app, something latest. So instead of that, we should have referenced it by its SHA, which is 256 digit unique. So instead of saying my app latest, we'd say my app at the rate SHA 256 and then colon ABC, right? That's a immutable artifact, and it generates a unique one every time. This means what you tested in staging is byte for byte identical to what's run in production. There will not be any surprises from a registry update. Rollback means again just deploying the previous digest. No rebuild, nothing required. Simple, straightforward. In this chapter, next we'll talk about consistent promotion workflows. Um, this is where container practices meet the delivery process, right? Every artifact travels the same four stage path, which is build and scan, dev validate, staging promote, production release, regardless of whether it's designed for a cloud server or a pharmacy terminal. Let me walk through what each gate looks like in practice. So at build and scan, tools like Trivy or Snake scan the image for known vulnerabilities, which is CVs. If a critical vulnerability is found, the build fails. No exceptions. The pipeline also generates an SBOM at this stage and attaches it to the image. And next, at dev validate, your integration test runs, but also policy as code tools like OPA Gatekeeper evaluate the deployment manifest, which is like, is the image running as non-root? Is a resource limit set? Like, right? Is the image referenced by digest, not tag? If any one of these fail, the promotion to staging is blocked. And next, at staging promote, smoke tests run against the production like environment. Load tests may run for services with known traffic patterns. For device deployments, a staging cohort of actual devices may receive the update first. And last, a production release. Signed artifact attestation is verified. You cryptographically confirm that is the exact image that passed all prior gates. Okay, it's nothing newly introduced, right? And if health check fail post deployment, the automated rollback triggers within minutes. Yeah. Um, again, and I want to quote the principles here, which is automated vulnerability scanning at build time, which we talked about in build and scan. Next, policy as code gates at every stage transition. Then assigned artifact attention attestation before production release. And finally, automated rollback triggered on every health check failure. So with that, we'll move to the next chapter, which is CICD and observability. Pipelines built for reliability at fleet scale. Okay, this chapter will explore how to design a CI/CD pipeline that stays dependable across large heterogeneous device fleets. Right. It also shows how observability provides the feedback loop needed to detect the issues early and validate the rollouts and maintain operational confidence. Under this, we'll see pipeline design patterns for complex release environments, then canary and cohort based rollout strategies, and alerting approaches that reduce noise and surface risk, and last, fleet scale monitoring for release health and stability. So one example again I'll quote here. Say, let's say we have 10,000, I think roughly 10,000 kiosk deployments across retail locations for CVS nationwide, and you push a new version of your kiosk software. In first 15 minutes, you see uh, elevated errors rates on 12 kiosks. Let's say, is that a problem with the software or a problem with those 12 devices itself? Right? How quickly can you tell? How do you prevent the rollout from continuing to the remaining other remaining 10,000 devices? If it's a software problem, these are fleet scale reliability questions that individual service monitoring can't answer. So the insight is that reliability at fleet scale requires observability that operates at fleet layer. You need to know the deployment health trends across your entire fleet, not just the health of individual instances, right? That requires a strong pipeline design, rollout strategies, and alerting built with the fleet scale in mind of from the day one. Okay. So with that, CICD pipeline design for enterprise delivery. So we have first one is about pipeline standardization. So a single shared pipeline template will be given across all teams to reduce the configuration drifts instead of maintaining individual configurations, and which enforces consistent quality gates without burdening individual squads. And the same quality gates and same template is maintained across all the services and all the teams. Next, layered health checks. We have usual health checks with the Kubernetes environment like liveness, readiness, startup probes, which are defined at the platform level, not the individual service level. Deep health endpoints expose dependency status, not just the process availability. And we have fleet level observability. Observability covers like metrics, logs, and traces are correlated at fleet layer. It's not like giving individual view of what the logs and traces are for different services and metrics. No, this is correlated across all together, and a single view is built. Platform wide dashboards surface deployment health trends, and not just at the individual surveys, overall as a platform. So after the pipeline designing principles, next one is about cohort based alerting and incident response. This is one of the most operationally impactful patterns, and I want to give you a clear picture of why. So we already talked about the example where 10,000 retail locations are. So on any given day, maybe 50 to 100 of them will have transient issues, maybe a brief network hiccup, a scheduler restart, or a momentary memory spike. Anything is possible, right? If you have alert on every instance anomaly, your on-call engineer gets 50 to 100 alerts on a quiet day. And on a heavy deployment day, imagine that number explodes. This is alert fatigue, and it's genuinely dangerous because engineers start ignoring the alerts and they miss the real ones. So in cohort based alerting, solve what we are going to solve. How we are going to solve. You divide your fleet into logical cohorts. The diagram shows canary at 5%, early adopters 15%, general at 60%, long tail at 20%. A real world canary cohort for a kiosk fleet might be 500 devices in a single test market. So you deploy to the canary cohort first. You measure error rates, response times, and crash rates across the cohort. Not per instance. This is across the cohort. If the cohort error rate stays below your threshold, you promote it to early adopters. If the canary cohort error rate spikes, let's say 8% of the canary fleet is throwing a new exception, that's statistically significant signal, right? Not just the noise. An alert fires, a human reviews it, and you halt the rollouts before it hits the all 10,000 locations. And a real example of the blast radius benefit: when your cohort alert fires, you immediately know the issue is limited to the canary 5%. You don't have to spend 20 minutes figuring out if it's really widespread or not. And triaging starts with known scope. And the A ready telemetry point is important for what comes next. So this is the structured cohort data, which is exactly what anomaly detection models need to learn normal patterns and surface the genuine anomalies. So that concludes chapter 3. Next, we'll see aligning platform architecture with AI era delivery, which is chapter 4. And this is where I want to zoom out and connect the dots. So everything we discuss, the single control plane, immutable artifacts, hardened containers, fleet observability, and cohort telemetry. These aren't just good DevOps practice. They are prerequisites for the AI augmented operations. And if I have to quote an example, you want to build an AI model that predicts deployment failures before they happen. Okay, let's say. So, which is also trained on historical deployment data. Okay, for that model to work, what you need? it needs consistent, clean, structured telemetry, right? If you are 50 services, all the instrument health metrics differently, the model cannot learn the patterns, right? So if your pipelines have different gate criteria, the model can't correlate the gate outcomes with production failures. That's the reason standardization, immutability, observability are what give the AI consistent data to work with. And another example, let's say AI assisted policy compliance checking. Okay. You want an AI system to flag potential compliance violations in the deployment manifest before they reach production. That only works if your policy as code is well defined and that is version controlled, consistency applied, right? Which is exactly what the single control plane gives you. Okay. The same principles that enable device agnostic delivery give you the data substrate that AI needs. Okay. This is real, not just a coincidence, I would say. They are both fundamentally about consistency and observability. Okay. Then we'll move to what are the practical patterns for AI era DevOps. Okay. So there are four practical patterns that emerge from this foundation, what we spoke until now. And first one is policy as code at scale. Again, a real world example is using OPA to enforce that no container image tagged to latest. So, and whichever is tagged to latest can be deployed to product. It cannot be deployed to production. That's the first one. That policy lives in a Git repository, gets reviewed like code, and gets tested in CI, and is applied by an administrator controller to every deployment across every cluster. Okay. Now, next one is about AI augmented incident response. A concrete scenario, let's say, your anomaly detection model, it trained on which trained on 6 months of cohort telemetry, learns that a specific pattern of memory growth in the early adopters cohort, which almost always precedes an OIM crash in general cohort 20 minutes later. Okay, let's say the model surface this pattern during a live deployment before any user facing the impact and triggers an automated hold. Your on-call engineer gets one actionable alert instead of a cascade of incident pages. Right. And next one is about the scalable delivery observation abstractions. Think of it like a API contract, right? Between the services what typically we have. The platform team publishes a deploy to production contract. You give us a signed, scanned container image and a deployment manifest, and we handle the promotion, health checking, rollback, observability. Okay, this is a contract between the engineers. The product teams don't need to know how it works internally, right? They just need to know what all included. They consume the contract. This is how you scale to 100 teams, even more than 100 also possible, without even the platform team becoming a bottleneck. And last, continuous feedback loops. So the deployment frequency, lead time for changes, change failure rate, the mean time to restore. These are your DORA metrics. And an AI era platform, they are not just reported after the fact, they feed back into the pipeline optimization as well, right? If your mean time to restore is creeping up, the platform surfaces it as a trend before it really becomes a crisis. So, with that, we are almost to the end of this talk, which is key takeaways. Four things I want you to take away. Okay. First one, standardize the control plane, not the endpoints. The endpoints will keep diversifying more device types, more edge environments. Your control plane is what keeps the governance intact as the diversity grows. So the example from earlier, as I said, one SBOM requirement, one policy change propagates everywhere. Okay, next takeaway, immutability and least privilege are non-negotiable. The log4j shell example, where organization with the provenance image respond in hours. Those without that had spent days on the inventory. That is one example. And next one is about observability must operate at fleet scale. Individual instance monitoring creates alert fatigue. We again discuss one example there, and misses the fleet level trends. So, whereas the cohort alerting model cuts the noise and speeds the triage, and it's the data foundation for the AI augmented operation. And the last takeaway, these patterns are the foundation for AI delivery. The anomaly detection model, the AI assisted compliance checking, which we spoke earlier, the predictive rollout halting, none of this work without the consistent, structured, observable platform we have been describing. Build the platform that right now, so and it scales with you as AI capabilities mature. So with that, I'll end presentation. So thank you, and I am open up for any questions.